In this video, we'll learn about some of the commonly used C++ primitive data types. These types are also sometimes called fundamental data types because they're implemented directly by the C++ language. The types we'll discuss in this video are the character types, the integer types, which include both signed and unsigned integers, the floating point types, and the Boolean type. It's important to keep in mind that unlike many other programming languages, the size and precision of C++'s primitive data types are largely dependent on the platform that you're working on and the compiler you're using. This means that as a C++ programmer, you need to be aware of your specific machine and understand how much storage is allocated for these types to effectively use them. The C++ include file climits contains information about the size and precision of the data types for your specific compiler. As you know, computers store information using a binary representation which consists of zeros and ones. And these fundamental type sizes are expressed in bits. The more bits allocated to a type, the more unique values that can be represented. Also, the more bits, the more storage that's necessary to represent that type in memory. In this table, you can see how many values can be represented in a given number of bits. The formula used to calculate these values is 2 raised to the number of bits power. So we can store 256 distinct values in 8 bits, 65,536 distinct values in 16 bits, over 4 billion distinct values in 32 bits, and over 18 billion distinct values in 32 bits. Now let's take a look at the specific primitive types one at a time. The C++ character data type is used to represent characters such as the letter A, X, and so forth. The character data type is often implemented as 8 bits, which means it can represent a maximum of 256 characters. This is plenty to represent the alphabets for many spoken languages. However, some spoken languages have thousands of characters, and in many cases, multiple symbols are combined to form single characters. In order to support these languages, C++ supports a wider character type that can be as large as necessary to represent these characters. Unicode is a common standard used to represent multiple character sets for any language. When we work with characters in this course, we'll use the char data type since it easily supports the Latin character set. C++ also supports the integer data types. Integers are used to represent whole numbers. Both signed and unsigned integers are supported. There are many variants of the integer data type. Let's take a look at some of them. The following tables show the C++ integer data types for both signed and unsigned integers. In addition to those shown in the table, it's possible to store both signed and unsigned integers in the character data type. Notice that some of the keywords in this table are bold and others are italicized. Also, typical sizes are included in the table. For example, if you want to declare a signed integer, you don't need to use the signed keyword, since by default integers are signed. Similarly, if you want an integer type that stores very large numbers, you can simply declare the type as long, and you'll get a signed long integer. If you want unsigned integers, that is, integers that are 0 or positive values only, then you're required to use the unsigned keyword. I know this may seem a little confusing with all the optional keywords, but it's not so bad if you just think that by default, all integers are signed. I know what you're thinking. Which ones of these do I use in my application? And the answer is, it depends. If you want an integer variable that stores ages, then you could use an unsigned int or even an int. If you want an integer to represent the number of kilometers between the planets, then you'd probably want to use an unsigned long. For most applications, using int is perfectly acceptable, but you do need to keep in mind the limitations, especially when you perform math on variables and store results in other variables, since the results may not fit into the variable you're saving to. This could cause an overflow. We'll look at a specific example of an overflow in live code at the end of this video. C++ also supports floating point types. These are used to represent non-integer numbers, such as real numbers like 1.2, 0.5, and pi. It's important to understand that computers have finite storage, and many real numbers have an infinite number of digits after the decimal point. Pi is a perfect example of this. In these cases, computers store an approximation of the real number. There's no way the computer can store numbers such as pi precisely. Floating point numbers are represented internally by the computer as signed numbers with a mantissa and an exponent. You may remember your scientific notation from school, 1.234 times 10 to the 7th power. That's the way they're stored internally. This isn't something you need to worry about since it's handled automatically internally, but it's important to know that these are approximations. There are 3 types of floating point numbers: float, double, and long double. Each has varying precision and size depending on the compiler. Note that long double can store very, very small and very, very large floating point numbers. The last primitive we'll learn about is the Boolean type. The Boolean data type is used to represent true and false values. In C++, 0 is false and any non-zero value is true. C++ also includes the true and false keywords that are often used with the Boolean type. As you can imagine, Boolean types are used whenever you need to know if something changes state. For example, game over, key pressed, is invincible. These are all good examples of using the Boolean data type, since their values can be either true or false. Great, now let's head over to CodeLight and see some of these primitive types in action. So now I'm in the CodeLight IDE, and I've created a project called Primitive Types that's in the Section 6 workspace. In this C++ file, I'm going to go over some examples of using the primitive types. We'll start with characters, we'll do integers and floating point numbers, and then at the end we'll do booleans. And I'll also show you an example of an overflow so you can see the typical behavior you get with those. I've written the code ahead of time and I've commented out a lot of it, and what I'll do is I'll uncomment and run pieces of it at a time so you can see it build. So the first thing we want to do is take a look at this first example here. This is a good example of using the character data type. My middle initial is a J, so the variable name is called middle initial, and it's of character data type, so it can hold a single character. The way that C++ represents single characters is with single quotes around the J. Do not put double quotes there, that would make it a string and you'll get an error. So what I'm doing here is I'm simply initializing the middle initial variable to J and then displaying it right here in the output statement. So I'll build and run. And I'm just going to click here, remember, so it doesn't ask me my choice all the time, and I just want to build and execute. You can see here it says my middle initial is J, exactly what I expect. Okay, so now let me uncomment the integer types here. The way that you can comment and uncomment lines very easily is just select the lines you're interested in and just press Control / or Command / on a Mac, and that will toggle between a comment and non-comment. Okay, so in this case, I've created a variable called exam score, and I'm initializing it to 55. Now, exam score is an unsigned short int. Remember, we have to say unsigned if we want our variables to be unsigned, but I don't have to say int, I can simply say short. So this is the same as saying unsigned short exam score. Okay, so I'm initializing that to 55, and again, I'll build and run. And now you can see my middle initial is still J, and my exam score was 55. Okay, in this case, we've got another number, and I'll uncomment that out. The number of countries represented in my meeting were 65, and I'm initializing it. This is a simple integer. By default, it's going to be signed. And here it's going to say there were 65 countries represented in my meeting. So let me run that again. I'm pressing Control F5 on Windows just to use the shortcut. And you can see here there were 65 countries represented in my meeting. Now in this case, we've got a much larger number. Let me uncomment these 2 lines out. So now I've got people in Florida. That's my variable name. This is the state I live in, and there are 20,610,000 people living in Florida. The last I just checked on Google. So I'm defining this as a long. I'm hoping that that fits in the long. It's a pretty big number. I'm pretty sure it does. Let's try that. So I'll press Control F5 again. We'll run it, and you can see there are about 20,610,000 people in Florida. Okay. Now in this case, how about number of people on Earth? I'll uncomment those 2 lines, and you can see my variable name is people on Earth, and there are about 7,600,000,000 people on Earth. Now, something that's interesting is as these numbers get bigger and bigger and bigger, they're hard to read, and it's really easy to forget zeros and so forth. So the C++ 14 standard allows you to use those little tick marks right there. You can put them anywhere you want. It really doesn't care. just to make it easier for you to read, it strips them out and just creates the number. If this doesn't compile on your end, most likely you're not using the C++ 14 compiler, you're using the C++ 11 compiler. You could set it to C++ 14, or you could just get rid of these little tick marks to make it compile. So when I run this, you'll see something interesting happen. I'm pressing Control F5 again. Notice I'm getting an error. The error says error narrowing conversion. It's trying to fit that number into a long, and it doesn't fit. This is one of the benefits that I mentioned about using the list initialization right here with the curly braces. Notice what happens if I did, but actually, you know what? Let me just run this first as a long, which is really what I want, because otherwise it's not going to fit. So now I've got my long, and I'm going to build and run this. And you can see there are about 7 points. You can see the number is correct. Okay. But if I did a regular initialization, like a C-style initialization with an equal sign here, or an assignment statement, something like that, and we'll go back to long, because we know it's not going to fit in a long. And I'll build and run again. Look what prints out. There are about negative 98999 people on Earth. That's an example of an overflow. But you also notice that we didn't get an error. That's one of the benefits of using the list initialization. If I use list initialization, it will catch those problems for me at compile time, which is really, really nice. So again, I'll compile here. I'll Control F5. Boom, there's the error. I know I've got a problem. I can fix it. So I'll make this a long. Okay, so hopefully that makes sense. Always use that list initialization syntax. It's so much better. In this case, I want the distance to Alpha Centauri. That's pretty far. This is, I believe, in kilometers. Yep, it's in kilometers, because that's what my output statement says. I'll uncomment these 2 lines. And let's run this. And you can see that the distance to Alpha Centauri is, and that's my number. That's correct. Okay, so that's a good example of an overflow. I'll show you another example of an overflow at the end of this source code that may not be as obvious as this. Okay, so here's a couple of examples using floating point types. Remember, these are real numbers. These are numbers with decimal points. So in this case, my car payment is $401.23. I can uncomment this out. Obviously, if I try to store 401.23 into an integer, I've got a problem, because the integer would only hold the whole number. So the 0.23 would get truncated off, and I could have a problem. Okay. So in this case, let's run this. And now you can see that my car payment here is $401.23. Okay. If I want to store a larger number, I could use a double. In this case, I'm just storing pi. In this case, I'm hard coding pi to be 3.14159. It could be obviously much longer. And in this case, it's a double. And you can see that there's pi 3.14159. I can also store very large and very small numbers using long doubles. So in this case, I'm storing 2.7 times 10 to the 120th power. That's a very large number. And I'm going to store that into this large amount variable, and then I'm going to display it. So let's build and run. And you can see 2.7 times 10 to the 120th power is a very big number. You can see it's actually storing that correctly. The last one we'll look at is the Boolean type. The Boolean type is a true-false value. So in this case, I'll comment that out. You can see I've got a variable called game over. Let me use the correct underscore style here. I've got a variable called game over, and in this case, you could see that I've been working on a project that's using camel case. Muscle memory kicks in. So in this case, I've got a variable called game over, and I'm initializing it to false. And then I'm saying the value of game over is, and you might expect that this would print out false here, but it doesn't print out false. What it does is it prints out 0. Because as far as C++ is concerned, 0 is false. If it was true, it would print out a 1. Now here's an example of an overflow that's not so obvious, and I'll comment that out. Here I have a variable called value1, and I've got another variable called value2. They're both short integers, and I'm assigning 30,000 to this one and 1,000 to this one. Those numbers will fit in those variables. But then I'm going to create another variable called sum, and I've got value1 times value2. Now, I know that the product of those, I guess I should have called it product, huh? Let me call it product just to be a little bit more correct here. There we go. So I know that the product of those two numbers does not fit in a short. So let's compile this. And you can see that the sum of 30,000 and 1,000 is some negative number. Obviously, that's an overflow error. Be very careful with these things. Make sure that, those two pieces each will individually fit in the shorts, but the product certainly can't. Okay. But notice the compiler is helping me here. The compiler is saying, warning, you've got potentially a narrowing conversion here. So don't ignore those warnings, as the compilers do a pretty good job about predicting problems that can happen. Okay, so that concludes this video. You can see some simple examples of creating variables, initializing variables, using some of C++'s primitive types.